this little video is have a quick look at the required practical. We're not going to go into too much detail, but we are just going to have a quick whiz through the required practical. So one of the ways that you can measure the effect of temperature on rate is by doing a disappearing cross experiment. So, for example, I want you to be able to discuss a disappearing cross experiment, and you will have come across these at GCSE. Why do you think this reaction that you've got here with state symbols can be used as a disappearing cross? So have a look at that equation and see what you think will be causing the cross to disappear. And if we have a look, there's a solid produced here, and that will be what causes the cross to disappear. So a precipitate of sulphur, precipitate is the word we use when we mix two solutions together, so two aqueous things together, and we end up with a solid. And it's that precipitate that's going to obscure our cross. So we're monitoring this by the time taken for a fixed amount of that sulphur to appear. So enough sulphur that makes the cross disappear. So there we go, it's the time taken for enough sulphur to be produced to make a cross disappear. And we measure that time on a stopwatch. This is called an initial rates method because what you're going to do is stop the stopwatch after something has happened that happens quite quickly at the start of reaction. So some sulphur is produced and enough sulphur to make the cross disappear, we're going to stop the stopwatch. We want the temperature that each experiment is carried out to be known as accurately as possible. So what we're going to do is we're going to take an initial temperature when we mix and a temperature when the cross disappears, and then we're going to use the average of those two. So what temperature was it on average during that reaction? So there we go, we're going to measure the initial and the final and find the mean. Okay, so there we go. So the method here is just a suggestion, and if you were asked about this experiment in an exam, they wouldn't want to know the exact volumes and concentrations because they can vary. They would want to know what you were going to do roughly. So you're going to put your acid in a water bath to warm up. You're going to put your thiosulfate in a water bath to warm up, and these will be in separate containers. That's quite important because you don't want to mix them until you're ready. And then you're going to record the temperature at the beginning and add your chemicals and start the timer simultaneously. So you're going to mix your chemicals and start the timer. You're going to stop it when you can't see the cross and record the time. You're going to record that final temperature so that you can measure the, work out that average temperature. Because of some of the chemicals in this not being very nice, we're going to use a waste container. We're not going to pour it down the sink. And we're going to repeat it for at least 5 temperatures. And we would need to be able to describe that in the exam as well. So the reaction in itself produces a toxic SO2 gas. So we don't really like that. What could we use to prevent this escaping? Well, we could use some sort of bung on our flask. Okay, so a lid or a bung on the flask. A sort of cotton wool bung would be the best thing because it would avoid too much of a pressure build-up but also stop the fumes coming out. Now this isn't much of a problem, to be honest, because SO2 gas is quite soluble, so it will dissolve into the solution, and so very little SO2 gas will be evolved. We're going to use a waste container or a stop bath, and that stop bath is going to contain some sodium carbonate, which we know neutralises acids, and some phenolphthalein, which is an indicator that's going to tell us when all our stop bath has been used up, so we can't carry on neutralising acid, all our sodium carbonate has gone. So this is going to be there so that the acid, any unreacted acid and sulphur dioxide can be neutralised. So this is going to be, because remember that we added acid in our reaction, okay? So this is going to be to neutralise acid and sulphur dioxide. We don't want to put those down the sink, and that's why we're going to have that there. So what would you do with your results? Well, your results would look something like this. You would have measured an initial temperature and a final temperature, and you'll be able to use that to calculate the average temperature. You'll have measured the time for the cross to disappear, but time is not what rate is. Rate is a measure of change in concentration over time. So 1 over time measures rate. It's not exactly rate, because rate would be change in concentration over time, but we're measuring the same change in concentration every time we're waiting for the cross to disappear. So we're measuring that same change every time, and therefore it's going to be proportional to 1 over t, and we're going to just be able to use 1 over t. So what I want you to do is fill in the average temperature and the 1 over t column. Just want you to pay attention to the instructions you're being given. It wants the 1 over t to 3 significant figures. So why don't you calculate the mean temperature and the 1 over t and fill that table in. Pause the video and attempt that now. So these are the numbers that I've got, so check that you get those same things, and notice I've given my answers to 3 significant figures. Now this could be quite tricky to plot on a graph. We can find it quite difficult to know how to use these numbers. So what we could do is take every single number and multiply it by 1,000. If we did that, this number would become 8.70, and if we wrote times 10 to the minus 3 at the end of that, it would give us back 0.00870. So if we wrote the times 10 to the minus 3 in the units at the side of our graph, we say every number should be times 10 to the minus 3. This becomes a much easier graph to plot. So it's much easier to visualise plotting these numbers on a graph than it is to plot these very small numbers with the zeros. Okay, so a much easier graph to plot. So what you need to do now is plot the graph on graph paper, and the sort of things the exam board will be looking for is making sure you label the axes. Now, I'm not going to plot this graph because I haven't got graph paper here, but you could do this. But on your axes, we would want to see the 1 over t, yeah, times 10 to the minus 3 in seconds to the minus 1. And along the bottom, we want our mean or average temperature, and we've measured that in degrees C. And you plot your points so that they can be clearly seen. So don't just use a tiny dot. We're looking for crosses or plus signs. Okay, and they should cover at least half of the grid. Now, what that means is not that you must absolutely fill the paper, if that means the scale becomes strange, but that your plotted points must fill at least half of the grid that you have designed. Okay, so they're taking up space on that paper in both directions. And the examiner will look at that. And this curve will curve up like this. A couple of things to note, where will it end? Will having 0 degrees C mean no rate? Well, that's an interesting question, because actually 0 degrees C isn't 0 temperature. So this graph probably won't be going through the origin, because the origin is not 0 temperature. 0 degrees C is 273 Kelvin, so it's still quite a lot of heat energy. Okay, so plot your graph and then have a look at your shape. It should be something like this. It's a pretty exponential increase of rate when you increase temperature. Let's have a look at some of the questions then, see if you can remember some of this from GCSE. So can you remember which one is the independent and which one is the dependent variable? I always find it's easier to think about the dependent variable first. What was I measuring that depended on something? So the time depended on something. It depended on the temperature. So the temperature was my independent variable. What things did we have to control? Well, we used the same concentration of reagents, because that would affect our rate if we hadn't, and the same volumes, so that we had the same moles reacting. So that these were the things we were controlling. Now, you would normally want to control anything that would affect rate, but surface area was irrelevant, there weren't any solids at the start. Pressure was irrelevant, there weren't any gases, we weren't using a catalyst. So of the things that were varying, we needed to make sure we used the same concentration and volume. So what's our relationship showing? So can you describe and explain? And you can go back to our collision theory lesson and think about what affects, how temperature affects rate. There we go, we've got temperature increases, then rate increases. There are many more particles with energy greater than the activation energy, so many more successful collisions. We have two reasons why the sulfur dioxide hazard is low. We already talked about those. So that ends the video on the required practical.